there are multiple processes. So currently we know what deadlock, right? So which means we know that there could be multiple processes. For example, this is like, I mean, these are the persons, but yeah, you can understand them like a process which are blocking each other for some reason, right? So this is called deadlock. Okay. Now, now we will see more about deadlock. So we have seen that, okay, one process, two process, let's suppose this is P1, let's suppose this is P2. These two processes are blocking each other because they are requesting some sources and which are not available. Okay. So this is a deadlock situation. Now let's just see more about deadlock. Okay. So let's see that how we can deal with deadlock. Now we know what deadlock, but how we can deal with deadlocks, right? The first solution is that just ignore the problem altogether. Second solution is deadlock prevention, then deadlock avoidance, then deadlock detection. Okay, so these are the solutions for the deadlock. Let's just see all of them one by one. Okay, so by the way, this deadlock will take the time will take the entire lecture. These are just definitions, kind of. Okay, this will not take much time, but yeah, this third point will take more of the time, which is, I mean, from the date point of view, also there has been many questions asked from this aspect. Okay. So the first solution is that just ignore the problem altogether. So which means we do not care about the deadlock. Just ignore the problem and pretend that deadlock can never occur. If that occur, then you can restart the system manually. Okay, if it is there, okay, then you can restart the system manually. Which means this algorithm is basically also called as ostrich algorithm. Ostrich is a word. Okay, that bird is basically putting her head in the sand. So basically, put your head in the sand and pretend that there is no problem at all, right? So do something like this: put your head in sand and pretend then there is no problem at all. Uh, would you wonder that this algorithm, okay, the ostrich algorithm, this is used by most operating okay, including Unix. So basically, most of the operating system doesn't care about dialog because it happens once in rare, okay, once in 5 years or once in 1 year or something like that, okay. I mean, it happens very rare, so that's why most of the operating system uses ostrich algorithm. Okay, so this algorithm is used by most of the operating systems. Okay, so you can say that this algorithm is used by most of the operating systems. This is important, which means most of the operating system doesn't care about deadlock. Okay, now let's see the next solution. Okay, next solution was deadlock prevention. So I hope the first solution is okay to everyone. This is just like you don't care about the deadlock. Whenever there is a deadlock, you just restart the system. Okay, this is the first solution. So what is the next solution? Next solution is basically saying that deadlock prevention. Okay. Now let's just see what is the solution, deadlock prevention. You might remember that we four deadlock, which means if deadlock is there, then these four conditions must exist, right? I mean, if by chance you negate any condition, then deadlock cannot occur. Okay, so in this solution, in this strategy, we will try to get one of this condition, right? First, tell me, is this possible to negate this exclusion? Is this possible? Is it possible to negate mutual exclusion? Means the resources, this is about resources, the resources are not shareable, resources are mutually exclusible. This is about resources. Can you do anything about resources? If they cannot do multiple tasks at the same time, then you cannot do anything about the resources, right? Basically you cannot do anything. This is not possible even to negate. Okay, so you can say not possible to negate because it is not in your hand, right? It is about the resource. If let's suppose the resource is mic, right? If only one person can speak on the mic, then only one person can speak, right? I mean, you cannot ask the two persons to speak at the same time on the mic, right? So basically it is not possible to negate, not possible to negate. I mean, if mutually exclusive resources, then they are mutually exclusive. Okay, if they're not shareable resources, then you cannot share, obviously. Similarly, the third condition is also related to okay, that is also not possible to negate. So basically, this is about resources. If the resource you can't preempt, For example, just imagine that someone is printing. Can you print and then take away in the between? If someone is printing, okay, then can you take away printer from take away from printer in between? Tell me, what do you think? No, right? No. So we cannot do it, right? So we cannot even negate this. I mean, if it is non-preemptible, it is non-preemptible. I mean, you cannot make it preemptible. Okay. So since it is also about the resources, so you can say not possible to negate. Okay. Not to negate. It's okay. Now, hold and wait and circular wait, we will see if it is possible to negate. See, what we are currently studying, we are studying strategies to deal with deadlock, right? So one strategy is that you don't care about the deadlock. I mean, this is obvious strategy and most easy strategy, and interestingly, this strategy is basically employed by most of the operating systems, right? This strategy is employed by most of the operating systems. Understood? Now the second strategy, okay, the second strategy is prevention, prevention. Okay, deadlock prevention says that you try to prevent one of this condition. Okay, if any of this condition does not occur, do you remember the legs of the table? Okay, if any of this condition you can prevent, then obviously deadlock cannot occur, right? So mutual exclusion and no preemption is anyway not in your head. So this is resource dependent. Okay, resource dependent conditions, right? That is not in even your hand. Okay. Now let's just see the other conditions, other two conditions which are hold and wait and circular wait. Can you negate them? This is the question. Negate them. So me just ask you if you can negate hold and wait and circular wait. Yes, we can negate them, right? So we can negate them. So let me just write it here. These two conditions we can try to negate. Okay, how you can negate hold and wait? So basically what you do whenever you are requesting something, okay, you release all the resources. I mean, you do not hold whenever you are requesting something. Okay. So basically you ask the operating system that okay, that whenever the process is requesting system, requesting anything, then ask the process to release everything that is. So how you can prevent this hold and wait? Me? How you can prevent this hold and wait? The answer is that whenever process request for some resource, ask it to release. I mean, you do not hold basically, okay? Release everything it holds. You do not hold and wait, okay? I mean, basically, whenever you're requesting something, then ask it to release everything that it currently holds. Okay. So this is how you can hold and wait. But obviously, this is not so effective. I mean, you can see the reason, or you can definitely understand why I'm saying so. Okay, this is not so effective. Why? Because if you're releasing the things, if you're releasing the resources that you already hold, then obviously like this is underutilization. I mean, this leads to, you can say, this is leading to underutilization of the things, right? So you can say this leads to this solution leading to leads to underutilization of resources, because you are releasing them, and without the task completion you are releasing them. So it's not a good idea, right? Can you prevent this circular weight? Okay, so basically I hope this all of these conditions are clear to everyone, that mutual exclusion and no preemption are resource based, right? If the resource cannot be preempted, if resource cannot be shared, then I cannot do anything, right? But I can prevent hold and wait by saying that, okay, whenever you are requesting something, let's just release all whatever I already have, right? That's how you can definitely prevent hold and wait. But obviously it's not a good idea to release the resources before the task completion. Okay, then the last thing that you can that you can attack, or that you can basically try to prevent, is basically circular weight. Okay, so let's just see how we can attack on this circular weight condition. So what we can do, we can impose some ordering. Okay, which means we can basically number the resources first. Okay, for example, r1 r2, first we will number the resources, and then we will impose the ordering. Okay, in the increasing order of the resources. For example, let's suppose there are two resources p1 and two processes p1 and p2. Okay, p1, let's suppose p1 already has, okay, p1, let's suppose, already has r1. Okay, or maybe let's suppose r5. p2 already has, let's suppose, r10. Okay, let's suppose already has r10. Now we will make sure that p1, if already it has r5, then it cannot request a number which is lesser than 5. Okay, it cannot acquire number which is lesser than 5. So if it wants, then it can only acquire the number which is greater than 5. For example, if it wants, it can request for r10. Okay, request for r10, but it cannot request for r4 or something like this, I mean earlier than r5. Okay, so P1 can request for R10 for sure. Now tell me, can P2 request for R5? Can P2 request for R5? See, if P2 is already having R10, can it request for R5? No, it can only request for R11, R12, something like this. Okay, it cannot request for R5. Basically, there cannot be a cycle. You cannot make a cycle. It is requesting this, this is requesting this. Okay, you cannot make a cycle. If you are always going in some order. Okay, let's keep it increasing order, decreasing order, doesn't matter. But if you're always going in some order, then you will always be having some directions. Okay, I mean some increasing order, right? I mean you can never ask some process to request for something lesser than what it already holds. Which means which means which means here I can say that p1 can request for r10, but p2 cannot request for r5. Okay, so here I can say that p1 can request for r10, but p2 cannot request for R5. Hence, there is no circular weight. Because of this, right? Hence you can say no circular weight. Okay. Basically, from the Galvin also, I mean, you do not need to read this. This is from Galvin. They are also saying the similar things, that you go always in the increasing order. Okay. Something like this. So basically, you always, I mean, the process resources are always in the increasing order. For example, if these are the, let's suppose, I mean, five, six processes, or whatever, like let's suppose 10 processes. These are the many resources, R1, R2, R3, R4, R20, like this, right? Now, if P1 is already holding this R3, okay, or already holding this R3, okay, let's suppose already holding this R3, and then at that point in time, P1 cannot request this request is not possible, this request is also not possible, okay? So how it is preventing? Because let's suppose P3 P3 holding, let's suppose R4. Okay, P3 holding, let's suppose R4. Then P3 cannot question R3 because it's lesser than R4. I mean, you always go in the increasing order, right? and then P3 can request for something like this. I mean, it can never form a cycle. You can never come back. Basically, there is some ordering that you are determining. That's all, right? So anyway, like what I'm trying to say here is that these are the four conditions that we wanted to prevent. First and third condition is not even possible to prevent or not even possible to negate. The second condition or fourth condition you can work on, right? That's all I wanted to say. Okay. I mean, this is not too much important, to be very honest. You just need to understand what I'm trying to say. Okay, don't worry too much if you are not understanding that. Okay, how to negate, how not to negate. It is just that these are the four conditions that we are trying to negate. So only thing that I'm trying to say is that if you want to prevent these four conditions, then somehow you can try to prevent. I mean, basically hold and wait and circular wait, you can work on that, right? Okay. Don't worry too much that how to work on that, but yes, we can work on that. Okay. That's all is important for us, right? So, so now if we go to the strategies to deal with deadlock, then first is that ostrich algorithm, just ignore it altogether. Second is that we try to prevent, okay, one of these four condition, right? Try to prevent one of these four conditions. Understood? Try to prevent one of these four conditions. Now let's just see what is deadlock avoidance. Okay, now let's just see what is deadlock avoidance and then deadlock detection. So deadlock avoidance says that we somehow make sure that deadlock will never occur. Okay, we will try to avoid deadlock. Somehow we need to make sure that deadlock is not going to occur anyhow. Okay, and deadlock detection is basically saying that in every 1 hour or every matlab, periodically, okay, in every 1 hour we will keep on checking if there is a deadlock. So we allow deadlocks. So basically, in the deadlock detection, we allow deadlocks. I mean, we will not worry about the deadlock doesn't happen. We will just keep on checking if there is a deadlock. Okay, and that's the deadlock detection that we will come later. But for now, let's just see what is deadlock avoidance. In deadlock avoidance, we just make sure the deadlock will never occur. Okay, somehow we make sure the deadlock never occur. So let's just see that how to make sure that deadlock doesn't occur. Okay. So let's just see that how we can somehow make sure the deadlock doesn't occur. So how we can make sure, basically before allocating any resource, we ensure that granting it will not lead the system in the deadlock. Which means it's like in Hindi, if you know that फूक फूक के कदम रखना, which means before granting any resource to the any process, I will make sure that कि आगे कुछ भी हो जाए but deadlock नहीं होगा. Getting my point? So before granting any resource to any process, I need to make sure that आगे कुछ भी हो but इस request को fulfill करने से deadlock नहीं होगा. Okay, that's what deadlock evidence is. Let's just see that how to do that. So deadlock evidence comes with the algorithm which is called Banker's algorithm. Okay. So let's see this Banker's algorithm and then you will get to understand this deadlock evidence clearly. Okay. That's easy only. Don't worry, it's not that tough. So basically, let's just consider a scenario that there are total 12 resources. Okay. 12 tape drives or 12 resources. Currently, these are the allocated ones, which means out of those 12, okay, 5 plus 2 plus 2, how many? 7, 8, 9. 9 I have allocated to P0, P1, P2. So basically, how many available? Available will be 3. I think, yeah, available will be. So I will tell you the terminology here. Don't worry. So now we are going to see Banker's algorithm, right? Now let me first tell you the recap that what we have been doing. I told you that, okay, these are the strategies to deal with the deadlock. Either you ignore it completely or somehow you make sure that those four conditions, one of the four conditions doesn't occur, right? So which is called deadlock prevention. Another is called deadlock avoidance. Here, here before we grant, we don't worry about the four conditions. Okay, we like those four conditions can happen, doesn't happen, we really do not worry about the four conditions. Okay, here in the third point, we really do not worry about these four conditions. We only make sure that whenever we are allocating some resource to some process, okay, at that point in time, we make sure that deadlock doesn't happen, and that is done by banker's algorithm. So let me just tell you how does it happen. Okay, so let's just see this example. Suppose there are 12 total resources. Out of them, I have, this is called allocated, this is called could ask for. Okay, we will be calling it need. Okay, these are the standard terms. I mean, in terms of the Galvin or any other standard book, so they call it allocated is a one of the column. Okay, and need is another column. Okay, so which means currently we have allocated 5. In future, need means future. Okay, in need, either you say need or you say future need. I mean, this is basically both are the same. Okay, you understand, like a future need. So basically in future, could ask for 5 more, it could ask for 2 more, it could ask for 7 more. Okay, I mean, currently these are the allocated, but in future they can ask for this many also. Okay, is this, are these terms okay to everyone? Now you need to first of all understand these terms. What do I mean by could ask for, or what do I mean by need? It, let's suppose this is the situation at 10 a.m. Okay, at 10 a.m. at 10 a.m. Okay, let's suppose these are the currently allocated. Okay, suppose at 10 a.m. these are the currently allocated. Can you tell me at 11 a.m.? Okay, can you tell me at 11 a.m. what could be the situation? I mean, at 10 a.m. I have allocated 522, right? At 11 a.m. P naught, P1, P2. P naught may ask for, okay, I'm just writing may ask for at 11 a.m. or after 1 hour, may ask for one more resource. Is this possible to ask for one more resource at 11 a.m.? Yes, P1 in future can ask for total of 5, but at 11 a.m. may ask for just one. Okay, and then at 12 p.m. may ask for 4 more. See, you should understand the meaning of this table. Okay, so this is currently allocated. This is the future need. Future need means could ask for. It is not necessary that it will immediately ask for 5. Okay, it may ask for maximum 5. It is not even necessary that in its lifetime it will ask for 5. Okay, it may ask for maximum 5, or 5 may ask for 2 maximum, may ask for 7 maximum, right? That's all these numbers means. For example, at 11 a.m., it could ask for 2, and in future, obviously, it will ask for 0. At 11 a.m., okay, out of 7, it could ask for, let's suppose 3. In future, let's suppose it is asking for 1. I mean, it is asking only for total 4. Okay, I mean, here it is given 7. It could be upper number. I mean, it is the maximum possible number or the future need. Okay, it is on the safer side basically. Okay, this 7 doesn't mean that 7 you are going to immediately ask, or 7 you will ask ultimately, I mean, by the process ends. 7 just means that in the worst to worst case, it may ask 7. Okay, in its lifetime, maybe immediately, maybe all of the 7. Is this possible to get to ask all of the 7 immediately? Yes, it is possible, right? But is this possible to ask for 8 immediately? No, 8 is not possible, because 7 is the maximum which I am claiming that this process will ask. Okay, so I hope this thing is little bit okay to everyone. What I'm trying to say, right? Okay. So now basically let's just go back to this table. That what this table is saying. Okay, so this table has two columns, allocated and need. Okay, don't worry too much. I hope, I think I have emphasized this too much, so maybe you are thinking that there's too much of mystery. There is not much of mystery. Okay, there is not much of mystery. They will just give you two things. Okay, they have to give you in all of these type of questions. They will give you two numbers. I mean, this total, obviously they will give you total available. Okay, total they will give you. Apart from that, what is the currently allocated, what they can ask in future, these two they will give you. Okay, in all of the questions. Now what we need to check, let me just tell you whether this system is basically is in deadlock or not. These kind of things we need to check. Okay, so first I will check available, how much is available. Out of 12, I have allocated 5, 2, and 2. So how much is available currently? 3 is available to you, right? 3 is available to you. Now, very, very simple algorithm, extremely simple algorithm. Okay, out of this available, which process demand you can finish? See, in future they can ask for 5, 2, or 7, right? So you can finish this P1 demand. So you can finish this P1 demand, right? So after P1 finishes, okay, this 3 is already available to you. Okay, this 3 is already available to you. Add one number to this 3. What is that number? What is the allocated to P1? Because see, 3 is already available to you. You can process, or you can basically fulfill this P1 demand in future, right? P1 I mean, it is possible that you may not be able to fulfill P0 demand if P0 is asking directly 5 or P2 is asking directly 7. But in worst case, even if P1 asks for directly 2, then you can fulfill this demand, right? Then also you can fulfill this demand if P1 is asking directly 2. So once this demand is fulfilled, then this allocated will be added to the available. Basically, this will be available now. Okay. So now the new available is 5. Is this understood to everyone? Let me know. New available is 5. Okay. Now what to do? Now with this 5, what need you can, so basically P1, you can assume that P1 is basically finished, right? P1 is finished, right? So basically you don't have to worry about the P1 because P1 has got finished, right? Now with this new available, which you can fulfill out of 5 and 7, obviously 5 you can fulfill. So which means P0 you can fulfill, right? So once P0 finishes, you will be adding whatever is allocated to P0. What is allocated to P0? 5, right? So you will be adding this 5. So now number is 10. Okay. So this is new available now, right? Now, obviously the P note got finished, right? Obviously the P note got finished, right? Out of this 10, can you satisfy P2 demand? Yes, you can satisfy P2 demand, which is 7. So now the new available will be 12, right? Obviously this is basically reclaiming. The 12 was the total one. So we have got 12 answer. Okay. So this is basically, you can say, after P2 finishes. After P2 finishes, you are going to add this 2. So 12 will be your new available. Okay. Now after all finishes, you will be having this as available with you. Okay. Are you getting what I'm trying to say here? So basically the thing here is that that whatever is the available, 3 is the available. With this 3, what you can fulfill? P1 you can fulfill, so add this 2. Okay. Now the new available is 5. With this 5, what you can fulfill after 5, between 5 and 7? 5 you can fulfill, so add this 5, because this will be ultimately this will be freed, right? So that's how you can say that first you can finish, basically first you can fulfill the demand of P1, then you can fulfill the demand of P0, then you can fulfill the demand of P2. Okay. I mean, in this order you can definitely fulfill the demand. So basically given this system, right? Given this system, P0, P1, P0, and P2 is a sequence for the system. Okay. So basically, let me just tell you what I mean to say. Given this system, given this whole system, right? And you already know what is the need, what is the allocated, right? So basically, given this system, P1, P0, and P2 is a way to go, which means this is a sequence in which you can definitely satisfy all of these needs, because the current available is how much? 3, right? I mean, out of 12, you have already allocated this much. So 3 is current available. Out of this 3, you can first fulfill this. Okay. Then you will be having 5, and then you can fulfill this. Then you will be having 10. Then you can fulfill this. Then you will be having this 2. Okay. So basically, you're reclaiming what you have already allocated. So P1, P0, P2 is a way to go. What does this mean? We should be understanding this. By the way, this is also called a safe sequence. Safe sequence. What does this mean? It means that whatever be the worst case, okay, this is the worst case sequence basically. Worst case means, see, as I told you, that this is the need, right? This is the future need. But it doesn't mean that they will definitely ask for two, they will definitely ask for five, they will definitely ask for seven, something like this. This sequence I have determined, assuming that in worst case, even if P1 asks for the maximum of two, and I mean they ask for maximum, they ask for all of this. I'm not assuming that okay, this is going to ask for lesser than two, or this is going to ask for lesser than five, or lesser than seven. Okay, I'm assuming that in worst case maximum they can ask for this, right? Even if they ask for this, okay, let's suppose at 10 a.m, at 10 a.m, okay, this is the situation, and at let's suppose 10:05, at 10:05 a.m, they ask, all of them ask immediately for this, okay, I mean 5 to 7. In that case, first you fulfill demand of P1, right? Then you fulfill demand of P0, then you fulfill demand of P2, right? I mean, this is the safe sequence. So basically, if you follow this sequence, there cannot be any deadlock. Getting my point? Slowly, you will get to understand what I'm trying to say. So basically, here, given this system, you can have a safe sequence, which means first you fill the demand of P1, then P0, and then P2. And very easily, you can fulfill all the demands. And in this sequence, if you do it, that's not an issue, right? So basically, the system is in safe state. We also call system is in safe state. Basically, a state in which there exists a safe sequence, okay, such that every process can complete successfully. Okay, then we say the system, this system, okay, this system is in safe state. So I can say that this system is in safe state because there is a safe sequence. Okay, so this system is in safe state. Understood? Now let's solve some gate PYQ. Using that, you will get to understand more. So they are saying there are total 9 resources that you have currently allocated. And see, I told you the currently allocated, and then they will give you need, right? I mean, what they can ask in future. Okay. So these two columns they will give you, but here, I mean, there are two three terms. Okay, one is currently allocated, another one is need, and there is also called a maximum requirement. Okay, which means this is basically max is, you can say need is need. They do not directly give you sometimes need. Need is basically maximum requirement. Okay, minus current allocated. I mean, instead of directly giving you need, they give you this maximum requirement, something like this. I mean, maximum you need seven or three you already allocated. So in future, what you may need is four, right? So basically, let's just see this question, that how to solve this question. Let me go to the next page. Total resources are 9. Very easy question. Okay. Once you are practiced with these kind of questions, it will be very easy. See, we always want need. So let me just park this maximum requirement on the side. Okay. Let me calculate need from this. So what is need? Can you tell me need for this P1? P1 maximum might need, I mean, maximum total it needs 7. 7 minus 3 is 4. Here this is 6. 6 minus 1 is 5, right? Here this is 5. 5 minus 3 is 2. Okay. Is this fine to everyone? So basically, this is the need column. I mean, you don't need now this maximum or something. I mean, this is not required. Okay. So I'm just throwing it away, right? I mean, this maximum or something, this is not required. You just need. Okay. Yeah. Now total 9 is available, right? Total are 9. I mean, total, sorry, not available. Basically, total you have 9, right? Total resources are 9. So how many available? How many available? 9 minus 3 plus 3 plus 1, which means 9 minus 7. 2 are available. Okay. Now, out of this 2, can you fulfill anyone's need? Can you fulfill anyone's need? Yes, you can fulfill P3 need, right? So you can say that P3 need you can fulfill. So after P3 finishes, you will be having three more, right? After P3 finishes, you will be having three more. So five is new available. Now, P3 got finished. Out of this five, can you fulfill anyone's? Yes, I think you can fulfill P2 or P1. Okay, doesn't matter. So first P2, and then you will be anyway having one more, which is six, and then P1, or doesn't matter, or then I mean P3 first. After that, either you can do P2, P1, or P3 first, and then P1, P2. I mean, these are the multiple safe sequence that you have. So you can say there are multiple safe sequences. Okay, multiple safe sequences you have. So since there is a safe sequence, the system will never be in deadlock. Okay, I mean, even if they ask for the maximum or something, then we can grant, and system will not be in deadlock. You will get to understand more. Don't worry about if there is any confusion, system in deadlock or something. Okay. Okay. So basically the system is in safe and it is not in deadlock. Basically, sorry, not in deadlock, which means B. Okay. So B is the correct answer here. Easy question, but yeah, B is the correct. So these are the multiple safe sequences are available. Okay. Very easy question, right? So how to solve these kind of questions? Need and what is the currently allocated, what they can ask in future. Need and currently allocated you should know, and then just check with the available. Okay, and then keep on reclaiming from the currently allocated, and then see if you can do something. Okay, don't worry, we will be solving more questions obviously, and then you can get to understand this type of questions very clearly. Okay. Now, before we move to the gate questions or the new questions, let me tell you a, a second pattern of the questions that they ask from these kind of questions. So basically, one is that they ask you given system is safe or not. Okay, so there are two pattern of the questions. You can say two type of questions are asked. Okay, one is that given the system, check if it is in safe state or not. Given the so basically you can say this is pattern one. Okay, this is pattern 1. What is this pattern? Given the system, check if system is in safe state or not. Okay, this is first type of questions. There are next type of questions also. What is that next type of question? So there is a pattern 2. Pattern 2 is that they say that okay, basically let me just tell you the example. Basically they will give the system, and then they will say that okay, obviously it has to be in safe state. I mean, first you have to check whether, I mean, pattern 2 is basically addition of pattern 1 plus something. I mean, they will definitely ask for the safe state, so ask for two things. Okay, here basically pattern 1 is anyway there, plus, okay, plus they will ask for one more thing. Okay, I mean, this safe state asking is anyway there. Okay, the safe state asking is anyway there, plus they ask for something else also. So basically here we have already checked that it is in safe state. Now suppose, now they ask next further question. Now they say this, now suppose that P2 request one drive and we allocate it to P2, will the resulting state is in a safe state? See, you need to understand this. Tell me, we have already figured it out, right? I mean, we have already solved. Is this in safe state or not? Tell me, is this in safe state or not? So answer is yes, it is in the safe state, right? Answer is yes. We have already checked it, and we already know what was the safe sequence. P naught, P1, P naught, P2. Okay. So P1, P naught, P2. This is the safe sequence also. We already know this, right? Now they are saying that that's fine. Okay. See, that's fine. First, you need to understand what does this mean. Okay. Can you tell me what does this mean of saying that this is the safe sequence? First, tell me what does this mean of saying that this is the safe sequence. It means that if you want, then you can fulfill all demands of P1. Okay, which means 2, and then all demands of P naught, and then all demands of P2. Okay, I mean, in worst case, even if they ask for 5 to 7, okay, let's suppose at the same time, at 10 a.m. itself, at the same time, they are all of them are screaming, all of them are asking for 5 to 7. I mean, immediately they are asking for this. In that case also, okay, in that worst case also, you can first fulfill the demand of P1, which is 2, and then P naught, and then P2. Okay, that's the safe sequence. But what if, okay, what if P1 is not asking currently? This is the safe sequence that I agree. Okay, there is no doubt in that. Okay, the P1 is a safe sequence that P1, P0, P2. This is a safe sequence, and P1 is the first one in the safe sequence that I agree. But what if P1 is not asked? I mean, P1 may ask at 11 a.m. Okay, but currently, let's suppose I'm at 10:30 a.m. I mean, at the current position. Okay, at the current position, P1 is not asking for anything. Let's suppose P2 asks for one resource. P2 asks for one resource. In that case, can we grant this permission to P2? This is the question. See, the safe sequence is okay to everyone, right? So here, so what the safe sequence is saying, that if P1 asks for maximum, followed by P not ask, followed by P2 ask, then we are very good. Or even if they ask immediately, then I can ask P1 to complete, then P not to complete, or P2 to complete. Now, even if P1 doesn't ask anything, let's suppose P note is asking at this point in time. Okay, then the safe sequence is saying that currently safe sequence saying that if P1 is not asking, okay, maybe it is asking, maybe it will ask in future, but currently P1 is not asking. Let's suppose only P note is asking for something, or only P2 is asking for something. Then it's better, okay, the safe sequence is saying that it's better to wait for P1, and let P1 ask, and then I will finish P note, and I will finish P2. Okay, this safe sequence is saying something like this. But obviously we do not have to wait, okay, for P1 to ask, so for P1 to finish, and then P note to finish, and then P2 to finish. This is not an optimal way, right? This is not optimal execution. See, safe sequence is not the sequence of execution. That's what you need to understand. Safe sequence is just saying that in this order you can finish. But do I have to finish in this order? Do I have to wait P1 to complete? Okay. And then only I can wait for P0 to ask, and then P0 to complete. And then I can wait for P2 to ask, and then P2 to complete. No, that's not the thing. So safe sequence is not the execution sequence. This is what you need to understand. What does the safe sequence then even telling me? This safe sequence is only telling me that I have, there exists one sequence. Okay, in that way I can finish the execution without any deadlock. Okay, so safe sequence, you need to first understand that safe sequence is not the execution sequence. Okay, it is not the strict execution sequence. I mean, you can definitely execute in that order, but it is not have to be followed, right? Is this understood to everyone? So safe sequence is basically saying, it says that there exists one sequence in which you can execute and finish without deadlock. You can uh, you can directly, let me directly write, you can finish without. So basically, now let's go to the real question. Suppose now P2 is asking for one drive. See, P1, P2, P1, P0, and P2. This is the safe sequence. Okay. I hope you understood the safe sequence meaning. Safe sequence says that, okay, if this is the situation, then in worst case, I may ask P1 to finish, then P0 to finish, then P2 to finish, and there won't be any deadlock. But suppose at this point in time, P2 is asking for one drive. Okay. P2 is asking, not P1, not P0. P2 is asking, can you give that one resource to P2? Okay. This is the question that they're asking. Okay. Don't worry about the safe sequence here. So they are saying that P2 is asking for one resource. Can you give that one resource to P2? Okay. So what we need to do? We need to basically we need to check what happens if you give one resource to P2, which means what will be the snapshot of the system. I mean, the similar table I need to make, but after giving one resource to P2. Okay. So you can say this is after giving. So in that case, these numbers will be changed. So in future, P2 can ask maximum for, I think, 6, right? And current usage will be 3, right? If I give one resource, okay? Is this fine to everyone? After giving one resource to P2, you will be having something like this. Okay. Here the safe sequence was something that's fine. Like it doesn't matter. Okay. Whatever is the safe sequence doesn't matter. Okay. But after giving one resource to P2, now you again find the safe sequence. Does there, I mean, you need to check whether there exists a safe sequence here or not. Okay. If safe sequence here exists, fine. I will grant this permission. Otherwise, I will not grant this permission. Okay. So it's very easy. Now tell me what is the available now? 5 plus 2, 8 plus 3, 11. Available is 1, right? Sorry, available is 2. 5 and 5, 10. Available is 2. Okay. Because total is 12. Available is 2. Okay. Now, with this available, obviously, you can finish this off. So basically, you will be having new available after P2. After P2, new available will be 4. Okay. New available will be 4. With this 4, you cannot either finish P0 or you cannot finish this P2, right? So that's why you can say this is P1. After P1, yeah, right? So that's why you can say that now you are stuck, right? So basically with this, okay, if I just give you this question and if I ask you the safe sequence, then you will say that, okay, now the new available is 4. With this 4, neither I can fulfill this nor I can fulfill this, so there is no safe sequence. Okay. I mean, P1 you can execute, but after that what? Okay. After that, let's suppose P0 and P2 immediately asking for 5 and 6, then it will be a problem, right? So basically there is no safe sequence. So you can say that after giving to P2, okay, there is no safe sequence. So this is unsafe state. Just a second. Yeah. So here the maximum column is redundant actually. Let me just remove it. It's not needed. So basically this is unsafe state. Okay. Why? Because after giving one here, okay, which means from 2 to 3 and from 7 to 6, after giving one to here, then the available is basically 2. With this 2, you can fulfill this. That is fine. Now available is 4. But with this 4, neither you can fulfill this nor you can fulfill this. So basically, giving P2 is a risky thing. It is unsafe state. Will it lead to deadlock? See, you don't know. I mean, see, I will tell you further, but for now just try to understand one thing, that we do not have any safe sequence. That's why we call that system is in unsafe state, right? Now, will it lead to deadlock? Just think about it. Just because it is unsafe? No, because this is the maximum worst case. What if it is just asking for 4 and get finished, right? Just asking for 4 and get, see, currently available after this, currently available is 4, right? What if it is maximum? What if it is just asking for 4 and then get finished, right? Then obviously there is no problem, right? So what I'm trying to say, that there are two pattern of questions. Okay, one is that they will directly ask you the safe state. Another is that they will write one line that, okay, now P2 is asking for one drive, or P2 is asking for one resource. Now tell me the safe state. So first you have to modify the table, and then you check whether the system is in safe state or not. So the pattern two is basically, okay, let me write in that way. I think that's better. So pattern two could be that instead of directly asking the safe state, instead of directly asking safe sequence, they first they give you, or maybe like right like this, they first ask you to modify the table and find safe sequence. Basically, both the patterns are almost similar. In first, they directly ask you safe sequence. In the second one, they do not directly ask. Okay, they write one more line, and then you first execute that line. Okay, they will write one more line. Based on that, you modify the table, and then then calculate whether it is having the safe state, whether it is in safe state, or in other words, whether it is having safe sequence or not. Okay, I hope you are getting the point. So basically, given a state, we can check whether it is safe or not, right? If the current state is safe, the process can determine. But then, okay. So I hope you are getting the point. Now let me just show you one thing, that in gate also they have asked both the type of questions. See, they've asked whether directly, okay, they've asked directly. They have asked you to modify the table. What will the system do? Request P node is requesting for one resource, okay, one unit of R1. They ask you to modify the table and find out the state is safe or not. Okay, so I will solve these questions, don't worry, but I'm just showing you one thing. Okay. See here, that here also in this question also, that they are saying given this, okay, they will give you everything, and then giving this, after that they will say that, okay, they ask you to modify the table. Okay, they don't give you directly modified table. They say that, okay, what if P not request for some resources like this. Okay, currently you might not be getting that what is the 002. It means that for type X, no need, for type by no need, for type Z, two resources you want of type Z. Anyway, like I will come to that point. But in gate also they have done it 1 2 times. Okay, so this pattern 2 has been asked in gate also. Pattern 2 is saying that instead of directly asking for safe sequence, they first ask you to modify the table and find the safe sequence. Is this okay to everyone? Okay, this should be understood to everyone, right? Now, Now let's solve a question which is dealing with multiple type of resources. Current Earlier it was just tape drive. Okay, it was just tape drive or one type of resource. For example, 12. Now I am dealing with here multiple type of resources, which means A, B, C are the three type. Okay, so these are the three type of resources. Now I need to check whether this system is in the safe state or not. So what I need to calculate? I need to first calculate need. Okay, max is not required for us. I need to calculate available is okay. Basically, available also you can calculate based on the total. If they give you total, you can calculate available, right? By the subtraction. I will tell you how. Don't worry. So basically, first let's just calculate need. Okay, allocated and need are the two primary things to calculate. Allocated they will give you, need sometimes they'll give you directly, sometimes you need to calculate using the I mean you need to subtract from the maximum, and then you will getting the need. Okay, so let's just see. So maximum 753. I mean for A7, for A type 753. So you can subtract 753 and the currently allocated is 010. So you can subtract it. This is 7, this is 4, this is 3, right? 743. So you can write 743. Let me write ABC first. Okay. So this is 7, 4, and 3. And from this 3 to 2, you can subtract this allocated. So it will be 1, 0, 1 to 2, right? 1 to 2. From this, sorry, this is 1 to 2. Let me write with another color. From this 902, can you subtract 302? I think you will be getting 600. 600. 9 minus 3 is 6, 0, and then 0, right? 600 you will be getting. From this 2 to 2, can you subtract this 211? I think you will be getting 011, right? You will be getting 011. From this 433, can you subtract this? You will be getting 431, right? You will be getting, I think, 431. 4, 3, and 1. Okay. So you need to calculate need. Okay. Now the maximum is of no use, basically. Once you calculate need, then maximum is of no use. Okay. Let's just remove this. Now that's very easy. Now what are the available? Just write the available. It's just that there are like three calculations which are happening in parallel. Otherwise, don't worry about it. Okay. I mean, this is just like an old system. So can you fulfill anyone's need? 332. I think you can fulfill this. 332. You can fulfill this also, right? Okay. Yeah, you can fulfill these two. So what you can do, you can definitely, I mean, fulfill in any order. So basically, ultimately, you will be reclaiming 200 and 211. Okay. So let me directly add 200 and 211. Or if you, I mean, you can directly add 200, 211 because ultimately you will be reclaiming this P1 after P1 finishes, and 211 is basically after P3 finishes, right? So let me directly do this. This is 3, this is 4, this is 5, 6, 7, right? 743 is your new available. Is this fine to everyone? This is your new available. And P1 and P3 are finished. P1 and P3 are finished, right? Now just check with the 743, what you can do. You can definitely finish this. You can definitely finish this. You can definitely 743. Yes, 7. You can finish everything, right? So yes, you can reclaim everything. So you can say anything or everything can be finished from here. So there are multiple safe sequences. I mean, uh, P1, P3, and then one of this. Okay, either P0, P0, P2, P4. Basically, the order will be something like this: P1, P3, and then P0, P2, P4. Okay. I mean, first one of these two. Okay, P1, P3, or P3, P1, and then one of these two. I mean, P0, P2, P4. So there are six combinations. So basically, you can say 2 into 6. There are 12 safe sequences. Okay. Don't worry about the combinatorics. I'm just trying to show you that yes, this system is in the safe state. Very easy actually. Okay. Just check with the available how which you can fulfill. Okay. What need you can fulfill. You first calculate need, and with this available, what you can fulfill. That's all you need to do, right? So P1, P3. So the state P1, P3, P4, P2, P1. So they're writing. I mean, there are multiple ones. So you can write anything. Okay. This is one of the safe sequence that you have. Okay. Is this okay to everyone? Isn't it too easy? Just write the need. Then see with the available, which need you can fulfill. Whatever you can fulfill, reclaim those allocated, right? And whatever you can fulfill, reclaim. If you can fulfill multiples, then reclaim at the same time multiples. Okay, just to make the calculation easier. Okay. Now with the same setup. Okay. Now let me even write the need directly. Okay. So we have already calculated the need from the uh what we say, from the max, right? So let me take this need. So basically, they are saying that I mean, they are asking basically second type of questions question here. What is the second type of question? Second type of question was that given, yeah. Second type of question was that given this state, they will first ask you to modify this table. Okay, they are first asking you to modify the table and then do the same kind of calculations again. Okay, can you modify the table? So they are saying 102. Okay, what if P1 request for 102, P1 request for 102, which means 122 it can maximum request. Just a second, let me make it a little nicer. Okay. See, 122 it can maximum request, but they are saying 102, which means let me just immediately modify this table. So P1 102, right? So what will be the need after 102? The need will be lesser, right? This one will be 0. You can subtract 102 from here. So this one will be 0. And then this is 2. And then this is 0, right? 0, 2, 0. Okay. And then you need to add 102 here, which means this will be 3. And then this is 2. 302. Okay. So it will be 302. Now you do the same thing. Okay. This is after P1. P1 gets 102, right? Once P1 gets 102, then the table will be modified like this. Now you need to do the same thing. Okay. What is the available? Available was 332. Okay. Let's just quickly do the same thing. Available was 332. Can you fulfill anyone's need? I think you can fulfill this, you can fulfill this, right? These two you can fulfill. So just P1 and P3, right? So 302, 211, you can reclaim. 302, 211, you can immediately reclaim, right? So this will be 6, 7, 8, 4, 5, 8, 4, 5. I think with 8, 4, 5, you can fulfill anyone else, right? So yeah, this is still in safe. Okay, understood. Still in safe. So basically, what I'm saying here that this is pattern two type of question where they will ask instead of directly asking you to tell the safe whether the system is in safe or not, they will ask you to modify the table and then they will ask the same question. Okay, the same question they will ask, but first they ask you to modify the table. Understood? Okay. By the way, we have already calculated. Okay, for this particular question, we have already calculated. Let me ask one question here. We have already calculated the safe sequence. Okay, this was a safe sequence for this type of for this system. Okay, this was the safe sequence. Now they are saying if P1 asks for something, okay, P1 asks for 102 or something, right? Then after that, will the system be still in safe state? Then without even calculating anything, without anything, with this just slide, okay, with this just slide, okay, with this just slide, even not with the slide, with this information only, okay, if you already know the safe sequence and if P1 is requesting, with this information only, you can directly say yes, it will also be in the safe state. Because safe sequence is saying that even if P1 asks for the worst to worst case, okay, then also I can fulfill the P1's need. Okay, then go to the P3 need, then go to the P4 need, right? So if P1 is asking 102, why not? If P1 is even asking 122 completely, then also the system will be in a safe state. I mean, you do not need to do anything. Okay, you can directly tell, right? Yes, I think there is a small mistake that we have done. Okay, the available should also be decreased. So from this 102, I need to basically, sorry, this will be 230. 230. Yes, the available new available basically, since I'm already granting, so the available will also be decreased 230. Okay, so this is basically new available because I've already granted. But yeah, with this 230 you need to check. Okay, 230, I think you can fulfill this. 230 you can fulfill this, right? So 302 211. Okay, so yes, you can fulfill this. So this is 567. Okay, this is 7. This is 3. 743. Okay, the same one. Okay, the same. I earlier also I got this because I was fulfilling P1 and P3 earlier also. Okay. Anyway, so basically, still in a safe sequence. So, but even without solving or even without doing anything, you can directly tell from this. Is this okay to everyone? From this information, you can tell that okay. See, if I already know the safe sequence and the safe sequence, the first part is P1, and then the question is about P1 only, then obviously yes, right, we can definitely fill P1. But if the question is about P3, if the question is about P3, then we need to basically modify the table and then we need to check. But if question is about P1, then we do not even need to modify the table. Okay, that's the difference, right? Because the safe sequence is screaming, it is yelling, it is again and again telling you the same thing, that okay, you can fulfill the P1 worst case, then P3 worst case, then P4 worst case, then P2 worst case, then P0 worst case. Okay, but what if P3 asks first? Then modify the table and check if there is still a safe sequence. Got it? Okay. Now let's solve this interesting question. This question is basically, I made this question. This, you can say, like, made by me. Okay. So let's just see this question. So they are saying that suppose that P1 to Pn be the only safe state of a system. Okay, be the only safe sequence, you can say. Which of the following is or always true? If P2 is the first process to request for some resources, then P2 will always have to wait. If P2 is first one, no, which is asking, this is a safe sequence, but if P2 is first asking, then P2 always have to wait. Do you agree on this? Do you think it always have to wait? No, right? No. Maybe you can grant and then check. Maybe you can grant and then modify the table and then check, right? It depends. Okay. Maybe you can grant, modify the table, and then check if there's just still a safe sequence. So P2 always have to wait? No. See, safe sequence doesn't say there's an execution sequence that P1 has to execute first. No. So that's why you can say this is false. P1 request will always be satisfied without even checking the requesting state after processing P1 request isn't safe or not. What do you think? Yes, P1 request will always be satisfied. That's the point, right? That is what the safe sequence is saying. Basically, P1 request will always be satisfied. Okay, P1 request will always be satisfied. What about option C? Process request will always be satisfied in the same order as a safe state sequence, and we cannot satisfy any out of order process request. What do you think? No, right? We can, maybe depends on after modification of the table, it depends, right? We can never satisfy any request coming from PN. No, we can satisfy it, right? We can satisfy. So D is also false. Only B is true here. Understood? So this question, the purpose of this question is to make sure that you understand what is the safe sequence. Okay, safe sequence is not the execution sequence. Understood? Now let's solve this question. This is also easy question. Okay, they are saying that, see, instead of giving you need, they give you maximum. Okay, don't worry, this is not the need, actually this is the maximum. Okay, you need to actually calculate the need. Okay, so current allocated is this, maximum is this. Then they're asking whether it is safe or not. So let me just do one thing. Let me go to the next page. Let me write the numbers here. This is P0, this is P1, let's suppose this is P2. Okay, See, this might look lengthy. It is not even lengthy. I mean, it is not even lengthy topic, or it is not even the lengthy calculation. Okay, it might look lengthy, but it is not lengthy. Immediately you can do it. Very easily you can do it. See, P note is basically having 102. So this is allocated are R0, R1, R2. So this is 102, then 031, then 102. Okay. The need we need to calculate. Okay. The maximum need is actually not need, it is the maximum only. This is the terminology. Now, this is the last term, maybe you need to know. Okay. After that, there won't be any shock. Okay. Don't worry, there won't be any shocks to you. So 412. Okay, 4. So maybe I can do one thing. Maybe I can just copy this table there. So 412 minus 102. So it will be 3, 1, 0, right? 151, 1, 2, 0. 1, 2, 3. So 0, 2, 1, right? This is the need. So you can now remove this. Okay. Now what is the available? Available is 220. Okay. Available is 220. Okay, with this 220, can you finish? Very, very easy questions actually. 220. See, either you can finish 220. Okay, you can finish, I think, P1, right? P1 you can finish. So you can reclaim this P1, which is 031. So what is the new available? This is 251, right? 251. Now with this 251, P1 has already finished. With this 251, you can finish this, right? You can finish this, which means now you will be reclaiming 102. P2 finish. What is the new available? 353. With this 353, obviously you can fulfill this, right? Now P note can be fulfilled. Understood? So P1, P1, P2, P note. This is your answer. If someone asks you the safe sequence, right? So P1, P2, P note, right? P1, P2, P note. This is your safe sequence. Understood? Now they're actually asking both patterns. They're now asking you the same. Now asking you that can you modify the table and find out the safe sequence again? Will the system? What will the system do? Is the request of P note for the 1 unit of R1 appears? Okay. So basically they are saying 1 unit of R1. P note is requesting 1 unit of R1. See, if the question is about P1, then we don't have to do anything, right? But the question is about P note, then obviously we need to check. So 1 unit of R1 means P note is requesting 0, R note, 1 unit of R, sorry, P note R1. So which means 0, 1, 0, right? Because this is R note, this is R1, this is R2. So basically, if you allocate from the available, first of all, this will be lesser, this will be 1. From the available, this will be 1, right? Now the need, the future need of the P note will also be lesser. This will be 0, right? And the allocation will be greater. So this will be 1, right? Okay. Now the table has been modified. Now can you solve the question again? See, with this 210, can you satisfy something? No, right? With this 210, you cannot satisfy anything. Okay. It doesn't seem to satisfy anything. With this 210, you cannot satisfy this because this is 3 and this is 2. So with this one, you cannot satisfy. So you can say if P note has requested, okay, after this is a table. Okay, let me write the table. This is the table we get after p naught request for 0, p naught request for 0 1 0, right? Just a second. Let me write here only. Okay. After p naught request for 0 1 0, this is a table. In this table, there is no safe sequence. Okay. So hence you can say that the request is postponed, okay, or not granted since it leads to the unsafe state. There is no safe sequence. So that's why we say it is unsafe state. Okay. Tell me. See, this is unsafe state. Okay, that's fine. That's fine. This is unsafe state. Tell me, is this a deadlock? Tell me, is this a deadlock? See, see, the problem with the deadlock is that we cannot tell with the need. Okay, with the need we cannot tell because need is always need could be the over approximate. Okay, if instead of need, okay, instead of need, if I just rename this, if I just say that okay, instead of need, I say request. Let's suppose I say request. Okay, let's suppose I say it is requesting. Okay, it is not anymore the future need, it is not anymore the maximum thing that they may needing in the future or something. It is the current request. Let's suppose I replace this term need with the current request, then immediately you say it is deadlock. The moment you say need, then you cannot say it is deadlock, you can only say it is unsafe state. Okay, it depends on the request that they are making. Okay, what if they make the same request, then yes, this is deadlock also. Are you getting my point? With this need, you cannot say it is a deadlock. Because of the word need, you cannot say it is a deadlock. The moment you replace this word with, let's suppose, request, these are the requests, not anymore need, then immediately you say it is a deadlock. Because need is not a request. Need is just a worst possibility. In future, it is unsafe state, but in future, deadlock may not happen because it is possible in future. It is just asking for one, not for three. It may be over approximate. So it is unsafe state, but not deadlock. You try to understand this. Okay. So what depends on the deadlock? It depends that what they're actually asking in future. If they're asking, okay, lesser than need, then may not be deadlock. Getting my point? If you replace this need with the request word, then it is a deadlock. Otherwise, if it is a need word, then it is not a deadlock, just unsafe state. So basically, I will just tell you in future. Okay, in future I will tell you that if it is a safe state, that's fine. But if it is unsafe state, then doesn't mean that always deadlock. Deadlock is a sub part of the unsafe state. Okay. So in remaining part, so what is this part? What is this remaining part? It depends. Why it is not deadlock? Because what if the process is not asking, okay, exactly for the need? If the process asks lesser than need, okay. So this part is because if processes ask lesser than need, right? Understood? If it is unsafe state, then there's a possibility of deadlock. It is not necessary there will be deadlock. Depends on what they're actually asking in future. Okay. So by the way, is this question understood to everyone? That was easy question only. Don't worry. Right. Now, let's solve this question. This is GATE 2014 question. So I'm writing this question in short. So basically, allocation, max, and available, everything is given. So they're asking you to modify it two times. Okay, they're asking you to modify two times, right? So you do this question by your own. I mean, we can definitely do this question. It's not a problem, but you can do it by your own also. Or maybe let me quickly try this question. Okay. So you basically they're asking you to modify the tables two times. Let's just quickly do it. Okay. Can you tell me the need? Let me write the need directly. Need will be this is XYZ. Okay. 8 minus 0. This is 8. 4. and then 2, and then this is 3, then this is 0, then this is 0, this is 1, this is 2, this is 2. Okay. And then okay, available is given to you. Now P note 002, they are saying first modify based on P note 002. So what will the available? Available will be 320, right? This is available. 002 means the need will be detected. P note 002. So the need will be like this. Need will be detected, and maximum anyway I don't need. Okay. And then allocated will be increased, right? So 002 means you will increase it by 3. Okay. Now quickly check 320. 320, I think you can satisfy this, right? 320, right? So basically, you will be anyway getting 320, so it will be 640. With 640, you cannot satisfy anything, right? So basically, this is not a good idea. I mean, this will lead to unsafe state. Okay, so the the first request is basically will lead to unsafe state. So request one, if permitted, does not lead to the safe state. So basically, the first request is leading to unsafe state. Okay, you can see 640, right? 640 is basically a problem. Okay, you can check the second request, which is 200. Okay, this is leading to the safe state. You can check it. You can modify the table. Okay, and then you can check it. So basically, this is the table. And now the second request is 002, I think, right? Second request made by P1 200. Okay, made by P1 200. Let me just tell you. Okay, made by P1 200. So what you need to do, need will be subtracted. So this will be 1. Allocated will be increased, right? So it will be 5, right? Available will be decreased. So new available, it is basically 122. Okay. With this 122, you can satisfy this. So basically you will be reclaiming. Okay. You will be reclaiming 211, which means 333, right? With this 333, you can satisfy this. So you will be reclaiming 522, which means 843, right? With this 843, you can definitely satisfy this, right? So basically, the new available is 333. Then you can satisfy this P1. Okay, you will be getting 520. So 853. Okay, this is new available. And with this, you can definitely satisfy P1, P note. Okay, then you will getting 001. Okay, anyway, I hope you understood. Okay. Now, if you already know the safe sequence, let's suppose somehow you already know the safe sequence, then based on that, you don't need to do anything. Okay. I mean, for this, I don't think the safe sequence is given. Okay. The safe sequence is not given. You can calculate the safe sequence, but that's fine. I mean, if you already know that, okay, P1 is, let's suppose, the first one in the safe sequence. Suppose, okay, you already know that P1 is the first one in the safe sequence, right? With this 322, maybe you can calculate the safe sequence. But if suppose you already know that P1 or P2 was first one in the safe sequence, then obviously you can directly grant the P1. Okay, you do not need to check anything. See, these two questions we have solved. These questions were from Gate, and both of the questions were related to pattern 2 also, which means they ask you to modify and then ask you to check whether it is safe sequence or not. Okay, great. So now we know that we know that how to do deadlock avoidance, which is basically using Banker's algorithm. This is the algorithm that we have seen. Okay, the available, and then we add these things, right? We add these things. So this algorithm is basically adding, and this algorithm is called Banker's algorithm. Now let's just see deadlock detection, the last strategy, which is deadlock detection. Okay, this is also easy one. The same thing that we have seen. But first, tell me, can you ever say that there is a deadlock? See, in this picture, see, there was, in this picture, can you ever say there is a deadlock? You can say this is unsafe state, but can you say there is a deadlock? No, right? I told you one thing, using which you can say, if somehow you get to know one thing, then you can say there is a deadlock. What is that somehow? Instead of need, instead of need, if I write request, the current request is this only. Okay. Okay, then we can say this is not anymore unsafe, this is actually a deadlock. Okay. So in deadlock detection, what we do, we detect the deadlock. Okay, we basically check the deadlock. But here in the deadlock detection, okay, what we have the similar tables. See, just one word is different. Yeah. So instead of need, basically we have similar tables only. Okay. Uh, in the deadlock deduction, instead of need, there is something called request. So basically, they will give you the question and they will ask you whether it is the system is in deadlock or not. Okay. If they ask you system is in deadlock or not, they cannot give you need. They can never give you need. They need to give you request. Okay. They have to give you request. Okay, which is the current request. Then they can ask you, is this system in the deadlock? The answer is yes here, because it was with the need, it was unsafe state basically. I mean, the with the available, what was the available, let me just check. See, available is 210, right? So let me just tell you that this is a deadlock system. Why? Let me just tell you. See, if this is the request, then can you fulfill anyone's request? 210, with this 210, you cannot fulfill anyone's request, right? I mean, there is no safe sequence basically. You cannot fulfill anyone's request. This is not anymore need. If it is need, then we say unsafe state. If it is request, then we say directly. We can directly claim about deadlock. Okay. So yes, the system is in deadlock. Similarly, you can find out whether this is in deadlock or not. Okay. So available is actually 000, right? Now, this is the request. Okay, this is the request first of all. Okay, then only you can talk about deadlock. Instead of need, they say request. That's the only difference. Okay. Okay, so don't worry here too much. Even if you check Galvin, in the Galvin, they are using the exact same terminology. They are, instead of need, they are writing request there. Here they are writing need. Okay, I mean, this is just, I think, one single paragraph or just one page, I think. Okay, and not more than half, or I think one fourth of page, three fourth of page, I think. Okay, so basically instead of need, they are just writing request. That's all. That's the only difference. Otherwise, don't worry about it. There has been no question asked from this topic, I think. Okay, as of now in gate. But still you should know. Okay, still you should know what is deadlock deduction. Basically, deadlock deduction is something that, suppose if we already know the request, these are the current request. Given the situation that, okay, these are the current request. Okay, suppose these are the current request, these are the available, these are the current request, these are the allocated. Given this whole system, can you tell me the system is in deadlock or not? Okay, then yes, we can tell. For example, here available is 000. With this available, I think you can fulfill this, so you can reclaim these two, 010 and 303. So you can reclaim 010 and 303. So this is the new available 313. With this 313, I think you can definitely fulfill this. You can definitely fulfill this, right? You can definitely fulfill this. So this is no deadlock, right? There is no deadlock. So this is P naught, this is P2. Okay, this is new available. Okay, this is no deadlock. Understood? Okay, so that's all, right? So now you know that what is a banker's algorithm. Now you know what is a safe sequence. Okay, so now you can solve actually all of the gate questions related to deadlock. Okay, that's all about the deadlock that we have to study in this session. Okay, so thank you everyone. Thank you so much for attending the lecture.